Welcome to Module 3, Lesson 4, More Writing Sums and Products as Sums. And just like always, and I will make it a habit of saying this before or at the beginning of every presentation, if you are not required to complete this entire presentation, please zip ahead to wherever you think you might have an issue. You may want to even try the lesson using just the lesson teacher guides with your parent teacher or by yourself, whichever is working for you. Okay, so please do not feel you have to suffer through this entire presentation if it is not necessary. Okay? So, with no further ado, let's get started. Okay, so to start us off here, I would like you to do this. I'm going to give you 2 minutes. Well, I'm not going to give you 2 minutes, give you as much time as you want. But I'd like you to go ahead and write equivalent expressions for all of these here. Okay, now these here, A, B, C, and D, you are going to go ahead and use the distributive property, okay, to then go from here to here. Okay, so you're going to use distributive property here. All right, and that, but the others, E, F, G, and H, okay, you are going to do just the opposite. Okay, you're going to take it in its expanded form there, and you are going to go back. So you're going to find here you need to find a common factor. Okay, find a common factor first, and make your way backwards. So we want to look at this distributive property moving this way to distribute, and then we're going to go back and more or less undistribute. Okay, so go ahead and give that a try and come on back as soon as you need help. Okay, so here are the first four, A, B, C, and D, and what I've done is I've just distributed the 2 times x to get the 2x, 2 times 5 to get the 10 in A, and done the exact same thing. We've done this many times, so I won't go into too much detail. But now let's go ahead. I'm going to go ahead and do E, F, G, and H, and if you want, you can try, or if you have it ready, just come on back. Actually, I think I'd rather do this with you. Okay, so again, what we have to do here is we have to find a common factor first in these expanded expressions here. Okay, a common factor for each and every one of them. So let's start with this one here with E, and we have 5x plus 30. We know a common factor to both 5 and 30. And actually, we're trying to get the greatest common factor. So we're actually trying to find the GCF, okay, the greatest common factor. And that would be 5. And so 5 is going to go on the outside of the parentheses, okay? And then we have our parentheses, and now we want to undistribute here. So this is going to be, it would be 5 times x would give you the 5x. And then we'd go plus, and then 5 times 6 would give you 30. Okay, so this right here is the kind of undistributed version of this expression right here. Okay, and they are both, of course, equivalent. This column here is equivalent to its companion expression on the other column. All right, 8x plus 8. Very easy to see that 8 is your greatest common factor there. And then we're going to need x because 8 times x is 8x. And then plus 1 because 8 times 1 is 8. Okay, 3x minus 12, we have 3 as our greatest common factor. And then 3 times x is 3x. We have a minus sign now. So 3 times 4 is 12. Okay, 15 and 20. Okay, we need greatest common factor. In this case, it's not going to be one of the actual numbers here. As you saw, these these all transferred over. It doesn't work that way here. So just remember, you're always trying to find the GCF, greatest common factor. And in that case, between 15 and 20 would be 5. But now 5 times 3x is going to give you 15x. Okay, and then we're going to add, and then 5 times 4 gives you 20. Okay, so if you did the distributive here, you would do 5 times 3x, and that would give you the 15x, and then 5 times 4, and that would give you the 20. Okay? Okay, here's another. I just want to, it's an extra one, it's not in your book, I just want, or your binder. Just want you to go ahead and write, just find some place in your binder to write an expression that is equivalent to 8x plus 4. So remember, you're going to undistribute, or what we would say you're going to, I would like you to factor completely. Factor this completely. Okay, so the opposite of using the distributive property is to actually factor. Okay, so we're going to factor it completely, just like we did before. Okay, so I would love to see what you came up with. I'm going to put a couple of possibilities down here, and I want to see what you think. How about something like this? Does that work? If I use distributive, 2 times 4x equals 8x, plus 2 times 2 equals 4. So it is indeed equivalent. Okay, so this is an equivalent expression to our original expression. The problem is, the only problem is that you were to, or we were to, factor completely. And that's really important. If you're going to factor completely, you've got to, you need to use the greatest common factor, because if you notice, right here, you would, you could actually, again, factor this. Okay, you can factor that expression as well. Okay, so what we would need to do then, and I think some of you probably knew this right from the get-go, we would find our greatest common factor, which in this case, over here, is 4. And then we'd have 2x, because 4 times 2x is 8x, plus 1. Okay? So this expression right here, inside of the parentheses, okay, is actually factored completely. Okay? We can't factor it any further. All right? There's no number other than 1 that is a common factor to both 2 and 1. Okay, so in that case it won't change anything. All right. Okay, so with that knowledge, go ahead and do these A through E, and what we want you to do is to rewrite the expressions as a product of 2 factors. Okay, as a product of 2 factors, which means you're going to unfactor it. Okay, you're going to go ahead and write it as an expression, as we have been doing in just beforehand. Okay, so we're going to rewrite the expression as a product of 2 factors. Okay, and this is the way we will. This is the way we describe what we're doing. Okay, so I'm going to go ahead and pause. You go ahead and do this and pay close attention to what you're doing. You know you're finding your greatest common factor. You're going to put that greatest common factor on the outside of the parentheses, and then you're going to have a sum in the parentheses. Okay, so here we go. Here are the answers. If you wanted to maybe just pause to shut me up and just go ahead and check those answers, or we can just go over them here. You might want to just check them. I'm going to take a little bit of time to do these, not very much, so you might want to just pause, check them, and then just move on without me. Okay. All right, so yeah, so that first one, A, greatest common factor, 8, factored it out, okay, and then we're left with 8 times 9t plus 1. In this case, the B was a pretty easy one. 11 was that greatest common factor, and it was in the actual original expression, which is always very good, makes it very simple. And then 5a plus 1. C, a little bit different. The greatest common factor actually this time was the coefficient, which we hadn't seen yet. And that was 36, and then times z plus 2. D was a little tricky, I'd say, because you might have looked at that and thought, golly gee, they don't have a common factor. But maybe some of you actually did the old divisibility rule, and if you did that for 144, 1 plus 4 plus 4 equals 9, and 9 is divisible by 3, okay? And then, of course, we know that 15 is divisible by 3, so 3 was that greatest common factor. So then it's going to be 3 times 48q minus 5. And then this one, this E also might have been somewhat tricky. The first one where we've actually seen two variables, okay? But we're going to look at those coefficients, and the greatest common factor, of course, of those coefficients is 3. And so 3, you have the 3 in the front of the parentheses, and then you simply have R plus S in the parentheses. Okay. Okay, this example 2 should be fun. In this example 2, you're going to let the variables x and y stand for positive integers. Okay, so x and y are going to stand for positive integers, and let 2x, 2y, and 8 represent the area of 3 regions in the array. Okay, and you can see those right here. 2x, 12y, and 8. So those are the area, okay, of the 3 regions. Determine the length and width. Okay, so we have the length here and the width of each rectangle if the width is the same for each rectangle. So this number here, this width number, is going to be one number. Okay, and then over here on the length side, I think you'll know what to put there. And if you don't, you'll see when you come back. So go ahead and give that a try, and then come back and check. Okay, so here are those answers. This width here is going to be 2, because what this is indeed is the greatest common factor of these 3 terms. Okay, of these 3 terms, that's our greatest common factor. So the way I can get these different length values or length terms is to just go ahead and divide each. So 2x divided by 2, of course, gives me x. 12y divided by 2 gives me 6y, and then 8 divided by 2 gives me 4. Okay, so the way this would look then would look like this. Okay, if we were to put that together. Alrighty. Okay, so on the heels of that, exercise 2 here asks you to write the product and sum of the expressions being represented in the rectangular array. So you're going to do exactly what I just did to that last problem. Okay, so go ahead and give that a try, and come on back. Okay, so here is the product and sum of the expressions being represented in the rectangular array. All right, so we have our 2. Okay, that's our width representation, and that's going to go here. And then inside we are going to have our length representations, which are 12D, 4E, and 3. Okay, so you can see, in fact, if you wanted to look at this, you could look at actually maybe look at this rectangular array, just imagine these as parentheses right there, and then whatever number you need, whatever symbol you need in between here, it's either a plus or could be a minus. All right, but that value will be shown as well. Okay, and then this next one here just asks you to go ahead and factor 48j plus 60k plus 24 by finding the greatest common factor of the terms, which we've been doing. So go ahead and do that, and you're going to actually write that expression in this form right here. Okay, and that's what you do when you factor. Okay, so here's what that expression looks like factored out, and it's completely factored. I have to tell you that maybe some of you did the same thing, but I started off with 6. I thought, okay, 6 and 8, 6 times 8 is 48. So I went, and I knew it wasn't 8 because 60 wasn't divisible by 8. So I went 6, and then 8j plus 10k plus 4, okay, because these would all distribute into these terms here. 6 times 8j, 48j, okay, and so on, okay. But I noticed something. I noticed after I did that, and if this did happen to you and you actually have this as your answer, it's not that it's not equivalent, because it is equivalent, okay, and it is factoring. In this case, you have indeed factored this this expression here, okay, but you have not completely factored. And whenever you see factor, we all want to think about that as completely factoring. So back to this one that I had, what I noticed that all 3, 8, 10, and 4 were also divisible by 2, okay? So if that's the case, you know this can't be complete, okay? It just can't be completely factored. So I had to go back and look at it. But actually, all I needed to do here in this case was multiply 6 times 2, and that gave me 12, okay? So, and then I looked at 12, and I know that 12 is indeed a factor of 48, 60, and 24. And I did realize after I wrote that expression down here that it was the greatest common factor, because all the terms inside the parentheses now, 4j, 5k, and 2, had no common factor except for 1, of course. Okay, so this was completely factored. So this is the correct answer. Okay, this is a real interesting exercise. It's exercise 3. And what it asks you to do here is for each expression, write each sum as a product of 2 factors. Okay, so and primarily emphasize the importance of the distributive property, and then use various equivalent expressions to justify equivalency. Okay, I'm not exactly sure what that means, but I'm going to do the first one with you right now. Let me go do a couple, and just to show you how how you might go about doing this. So what I do notice in this first one, and you have to look really, really carefully at all of these expressions, okay? Because you have what you have here is you have two products, okay? You have 2 times 3, and then you have 5 times 3. So in this case, what you notice is that you have 2 common factors, okay? And since we have a common factor, we can easily do this, 3, and then in parentheses 2 plus 5, okay? And the reason we know we can do this is because we know the distributive property. And then if we did the distributive property, we would go, and we won't actually multiply these, but we'll just write them again as multiplication expressions. This would be 3 times 2, and then that would be plus 3 times 5, okay? And these are the same as these here, okay? Because we know it does not matter in which order we put our multiplication, put our numbers in a multiplication sentence or expression. Okay, so you can see when you have that common factor in the sum of two products, which we have here. We have the sum, because there's that plus sign, the sum of two separate products, and the product expressions, and those product expressions have a common factor. Put it like that, and then you have either 2 plus 5 or 5 plus 2. Okay? Now this one here, the one right next to it, you'll notice B. You notice you have 1, 2, 3 similar expressions. Okay, so if you have 3 similar expressions, actually identical expressions, okay, identical expressions, you know that that is addition, and just like 2 plus 2 plus 2 is the same as 3 times 2, okay, this would work the exact same way, because now we have 2 plus 2 plus 2 plus 2 plus 2 plus 2. So we have 3, 2 plus, I said 2 plus 2, I meant 2 plus 5. 3 times 2 plus 5. Okay, so this is equivalent to this right here, because that just goes on the on the whole rule that multiplication is multiple, or I forgot the term, many additions. Okay, repeated addition. Yeah, repeated addition. Okay. All right. So how about one more? Let's take a look at this one here. Let's look at C. Then I'll let you go. See if you can do D, E, F, G, H, I on your own, and come on back. Okay. So what we have here in C is we have 2 times 2 here. Okay. That's one product, a product expression. Okay, and then we have an addition. Then we have 5. Then we have 5 times 5 plus 2, and then another 5 plus 2. Okay, so we can start by rewriting this this expression. Okay. Oh, sorry, I got to start over on C here, because I said 5 plus 2 at the end instead of 5 times 2. So anyway, with this one, it's a little tricky, and that's why it's a good idea we do this together. What we have here is that we can, firstly, it'd be a good idea to go ahead and rewrite this so we can put all of our multiplication together. And again, we can commute different parts of this, and we can move things around. So if we rewrote first as 2 times 2 plus, then we had that 5 times 2, okay, and then plus 2 plus 5, okay, 2 plus 5, and that really doesn't matter so much, this 2 plus 5, but you'll see why I did this. Actually, you know what? Why don't we not do this first, and then we'll change it later, okay? Because this is what it would look like originally if we just commuted, just moved expressions around, okay? Because we can do that as we are talking about multiplication and addition, okay? So now what we can do here is we can actually take a look at these first two. So first two expressions, the 2 times 2, and then the 5 times 2, and we can, like we did in the first one, in A, we can see that we have a common factor, okay, and the common factor being 2, all right? So those two expressions have a common factor. Now this, I mean, the way these look, I mean, this could be written with parentheses around it if you'd like to make it a little bit more understandable to you, and to make those two expressions look similarly. And they could also be without parentheses, just like A is right here. Okay, A over here, which is written without parentheses. These could be written without parentheses as well, because that right there with the parentheses is going to be the same as this here. Okay, 2 times 2 plus 5 times 2. Okay, that is the same. All right, so like we did in A, we know we have, again, like I said, the common factor here. So then we can pull that out, and then we could write this as 2 times 2 plus 5. Okay, 2 times 2 plus 5. Just like we did over here, we had 3 times 2 plus 5, because we had our common factor of 2, a common factor of 3, and here we just have a common factor of 2. Okay, and now we can add, and if you'll notice, the reason why I want to change these around, because I can, because they are addition, and they are commutative and associative, all right? If I did this, 2 plus 5, okay, what I notice here is now I have 2 plus 5s here. I have 1 2 plus 5 here. So altogether I have actually 3 times 2 plus 5. Okay? So this initial expression here, after I have used my associative property, my commutative property, and went ahead and used my sums as products of two factors, I end up with this, which is kind of interesting, is exactly the same as this over here. Okay? All right. Okay, so those were three different looking expressions to begin with. And gosh, do you know what I just noticed? And you probably noticed this already. These are all the same. Wow, that is so funny. Yes, they are all the same. They all actually boil down to, or all factor down to, the same actual final expression. So anyway, would you go ahead and do D, E, and F, G, H, and I, and hopefully there are no surprises. Okay, and come on back and then give it a whirl. Just give it a whirl and then come back and we'll check them. Okay, well, for D, E, and F, it looks like they all turned out to be the same factored expression. Okay, and again, F was, D and E, pretty clear to see. Two products, common factors, and then factor that 3 out, and you had 3x plus 5. Okay, and E was similar, similar to B in the sense that you had the 3x plus 5s, and that looks like that, factored out. And with F, was again, the way I did it was, exactly similar to C. Well, not exactly, but very similar, because just like 2 times 2 is a product, 2x is a product as well, okay? But it just has a variable attached to it. The 2 has a variable attached to it. So that 2x and that 5 plus x, okay, those two, they both have common factor, which is 2, okay? And so therefore, that factored out this way, 2 times x plus 5, all right? Because we had the 2 here and the 2 here, and then we had the 2, and then they have the x, and then the 5 to add in the parentheses. The 5 plus x did the same, but I just changed the order of that 5 plus x because it is the same as an x plus 5, and then if I added this x plus 5 plus these 2 others, I would get 3 of those. And there we go, 3x plus 5. So go ahead, G, H, I, do them, come on back. Okay, so hopefully after you did G and got 3x plus y, I hope you didn't just pencil in 3x plus y for the next two. If you did, of course, they would have been correct, but it would be better to know that you know what you're doing. H, again, is pretty simple. You have 3x plus y's, and therefore you can write them like this, factor them, simplest form. And then the 2x, and then I, what I did is I just moved this 2y from the back to right next to the 2x. Okay, then I could factor out that 2 because it was a common factor right here and here, and that became that. This, of course, I could flip around to be x plus y, and actually why don't I just do it down here just so you know. But those are the same, okay, y plus x and x plus y exactly the same, okay, because 1 plus 2 is the same as 2 plus 1, all right? And then again I had 2x plus y is here, had another x plus y, and I'm adding those, and then I end up with 3x plus y. Okay, so example 3 is now going to give us a scenario, and we're going to have to work with the scenario, and let's go ahead and read the problem. A new miniature golf and arcade opened up in town. For convenient ordering, a play package is available to purchase. It includes 2 rounds of golf and 20 arcade tokens. So we have 2 rounds of golf, 20 arcade tokens, plus $3 off the regular price. There is a group of 6 friends purchasing this package. So if we let G represent the cost of a round of golf and T represent the cost of a token, we are going to go ahead and then write 2 different expressions that represent the total amount this group spent. Okay, total amount this group spent. Then we're going to do some explaining, but let's first pay attention, or pay particular attention to writing these 2 different expressions. Okay, 2 different expressions. So if you can, just go ahead and you could use all this pertinent information. That's usually the items that include numbers in front of them. 2 rounds of golf, 20 arcade tokens, and then you get the $3 off regular price. There's 6 friends, and then we have we're using the variables G for golf, a round of golf, and T to represent the cost of a token. All right. So go ahead and write 2 expressions, 2 equivalent expressions that can actually describe or represent the total amount this group spent. Well, the simplest way to write this, I believe, is this expression right here, and real simple, and actually a nicely factored expression as well. Okay, because we have 6 friends. These here we have our 6 friends, so we know 6 people are going to purchase this package. Therefore, I just put my 6 here, okay, because that is what I'm going to multiply everything inside of this parentheses by, because everybody is buying the same thing. Okay, so what are we getting? What are they getting? Well, they are getting 2 rounds of golf. Okay, therefore we have 2G. All right, so there's our G, and we have our 2 rounds of golf. There's our 2G. Okay, and then we also know that they are going to get 20 tokens. So we have T for our tokens, and there is the 20 arcade tokens right there. So that is where we get our 20T from. Okay, and again, this is for every one person is the same. Now, on top of that, they are going to get $3 off. So we're going to take away that $3. Okay, minus $3, because we have $3 off. Okay, so this G is going to be this represents the price of a, so I'll use a different color here, black. This G is the cost of a round of golf, and this T is the cost of a token, right? This expression doesn't tell us how much each person is going to pay, but it is an expression we can use once we do get the price of the golf and the price of a token. We can plug those in, and we can indeed come up with a total. Okay, these expressions describes the situation right there. Okay, that I think, of course, like I said, is the simplest one. All right, a second one is pretty obvious. Well, maybe not so obvious, but if you went ahead and used distributive property here and distributed everything out, 6 times 2g is 12g, plus 6 times 20t is 120t, okay? And then 6 times negative 3 is negative 18, okay? All right, so this right here, this first expression, they're different, okay? So here's this explaining how it describes a situation in a different way. This second one, the one we just wrote, is very clearly a description of what the whole group pays. As soon as we find out that golf round price, and as soon as we find that token price, we can go ahead and plug those in, and we can come up with the total price. What this first one allows us to do, though, it allows us to separate it out, because once we plug in this middle, we can figure out what each player pays, each friend pays themselves, and then we can multiply that by the 6 friends, and we could also get our total, okay? We have, in the parentheses, we have what is represented by 1 friend, and then we have the 6 outside because there are 6 friends. This does not differentiate in that sense, okay? But they are still equivalent, okay? They are both equivalent expressions. And before we move into to exercise 4, first want to just talk a little bit about this idea. So what does it mean to take the opposite of a number? Okay, if you remember, we have talked about this quite a bit, not too long ago. Okay, the opposite of a number, when we talk about the opposite, we can think of both the, remember, additive inverse, okay, additive inverse, or the multiplicative inverse, okay? So we can think of both of these, okay? So, for example, if I asked you then, what is the opposite of 2? Okay, what is the opposite of 2? It's very easy to know that the opposite of 2 is negative 2. Okay, because that 2 and that negative 2 together are 0. Okay, and that is the idea of the additive inverse. Okay, so if you have, then if I ask you what is the opposite of negative 2, then you would know it is 2, because it is the additive inverse of the other. Okay, so yes, the idea of opposite in terms of additive inverse. Okay. Okay, and what would be negative 1 times 2? Okay, and we know by now negative 1 times 2 is going to be negative 2. Okay, And similarly, negative 1 times n is negative n. Okay, and that in that case is our multiplicative inverse. Okay, the multiplicative inverse, because we've taken both. In this case, we've taken both the 2 here, and the n, and we've multiplied both of those by negative 1. Okay, and when multiplying by negative 1, that is going to give us the multiplicative inverse of the number we began with. Okay? All right, so we have additive inverse is what causes the original number to be 0, and then multiplicative inverse is actually just multiplying something by negative 1. Okay? Now, so let's go ahead and let me ask you this here. So we have an expression 2a plus 3b. Now, my question to you is this, and again, this is all leading up to the following exercise, exercise 4. What two mathematical expressions would represent the opposite of that? Okay, so what expressions would be the opposite? Again, the opposite of this one right here, this expression 2a plus 3b. Okay, so firstly, one simple way to write it might be just like we did before, putting a negative 1 in front of the expression. Okay, so this represents the opposite of this, okay, simply because we have applied that negative 1, which creates the multiplicative inverse of the expression. Okay. Similarly, what we can do, and we don't usually use negative 1, okay, in that case, because we don't usually use 1 as a multiplier in front of an expression or in front of a variable as a rule. Okay, so this expression more simply or more correctly could also be written just simply like this. Okay, simply like that. Negative 2a plus 3b. Okay, and this negative sign here in the front tells us that everything inside of these parentheses will be the opposite of what is in there right now. Okay, so if we were to continue this and expand this again, this would look like negative 2a minus 3b. Okay, so this would be equivalent to this, which was equivalent to this, but this we want to pretty much stay away from right there. Okay? And furthermore, we could also write this one here, negative 2a, remember, plus negative 3b, such as that. So now again we keep our terms separate. Okay, so now using what you've just learned, go ahead and do these two problems here in exercise 4. Okay, so the first one asks you, what is the opposite of, in parentheses here, negative 6v plus 1? Okay, so go ahead and do A. Okay, so hopefully you came up with this here first, because this would be the first step, because it's really, really helpful to understand what exactly this little negative sign means here. Okay, we have that negative sign, and sometimes it means minus, sometimes it means opposite, And in this case, it means opposite. So always this and this, they go together, okay? So the opposite of this expression here could very simply be written like this, okay? We can go further, it is true, but for the meantime, that is correct. Now, if we want to go further, B here asks us to use the distributive property and write an equivalent expression for part A, and probably what we would consider a more correct problem. Okay. Now, distributive property, we have this negative sign outside of the parentheses. We're going to just multiply it, because what it is a negative 1. Okay, as we had said already. So negative 1 times a negative 6v is going to be, of course, negative times a negative is a positive, 6v. A negative 1 times 1 is negative 1. Okay, so this expression here is probably most correctly written like this, 6v minus 1. Okay, so that is the opposite of that. Okay, those are opposites. Now you might have gone right from this this one to this one directly, having skipped this. Okay, and some people might. If you know that if you know that well, that's good. Okay, so example 5 asks you to rewrite 5a minus 5a minus a minus 3b in standard form. Okay, in standard form, which is going to get us down to something plus something. Okay, we're going to undistribute it. All right. So justify each step, applying the rules for subtracting and the distributive property. Okay, so paying attention to the rules of subtracting and the distributive property, and write those explanations down if you can. All right. Okay, so go ahead and do that and come on back. Okay, they had recommended doing this in a few more steps, but I found 3 steps to be sufficient. Okay, so first I just went ahead and wrote this out as using the subtraction as adding the inverse. So I went ahead and put 5a, and I put plus, and then put negative a minus 3b. Okay, which is right here. Okay, instead I just added my plus sign there. Okay, and then moving there, what I did is I just, after that, step number 1 and then step number 2 here, I just went ahead and distributed out this negative sign here, which is actually a negative 1. Okay, that's a negative 1 in fact. Okay, that negative sign. So negative 1 times a was negative a, and then negative 1 times negative 3b is a positive b. So that was plus 3b, positive 3b. Okay, so now I have left with three different terms separated by plus signs. Okay, and if I combine, well, that was a distributive property there. Now if I combine like terms, I take my 5a and my negative a. If I add those together, and I end up with 4a. And then my 3b is there, so 4a plus 3b is my final answer. Okay, exercise 5 asks you to expand each expression and collect like terms. Okay, so you're going to come up with an answer that's similar to the answer we just came up with down here. Okay, in similar form. So go ahead and do those and come on back for A and B. And boy, B looks real tricky, but don't let it trick you. Okay, so A here. What I did first, I did again subtraction as adding the inverse. I just took this apart, and again, once you get to know this real well, you're probably going to skip this step, but it's good to see it now. What I did is I took my 2p and then just added that plus sign, of course, inside this parentheses, plus the negative 3q, which is just this, shown as a sum instead of a difference, okay? And then I just went ahead and distributed, all right? So negative 3 times 2p is negative 6p, plus, of course, I'm talking about sums now, and negative 3 times a negative 3q is a positive 9q, okay? Because negative times negative is positive, right? And that, again, was the distributive property, and there is my final answer, okay? Expanded answer. All right, for B, again, it looked real tricky, but not really, okay, because I have my negative a here, but now instead of my being a difference, I've made it a sum, and so I did added, and then I had my negative a minus b, because that is just this here, okay, put into, actually I don't like that thing, it's just this here, put inside the parentheses, okay? So I still have my negative a, and then my plus, and then I distributed out, because I distributed using that negative sign, which is actually negative 1. So negative 1 times a is negative a, and then negative 1 times negative b is positive b, because a negative times a negative is positive. Then if I go ahead and combine like terms, okay, which is the next thing I did, I took my negative a plus another negative a, that gave me negative 2a, okay, and then I still have my b plus b. And that is my final answer there. So in closing, the biggest difference between this lesson and the lesson that preceded it, lesson 3, both of which dealt with writing products as sums and sums as products, okay, was this idea of taking the opposite of a term or factor, okay. We took something like this, we took the negative, that's one of the last ones we did, negative 3, 2p minus 3q, okay, and we went ahead. So this right here, as you can see, is a product because it multiplies this expression times this, or this term times that term, okay, because this is actually one term inside of here, okay, inside of a parentheses. It's considered one term. So this problem is, or this expression is a product, okay. So what we wanted to end up doing is write that as the sum of two numbers. So one of the questions, the biggest question, is that when you write products as sums, what is happening when you take the opposite of a term or factor, okay? So what we multiply that factor by negative 1, okay? We multiply it by negative 1, and to do that, when we're using our distributive property, remember that we had our negative 3, and then we did plus, okay, and then we had our 2p, and we added that to a negative 3q. Okay, so there were a few different. Actually, this wasn't a. This is still a product here. That stays the same. Okay, so inside here we wrote our. We took our the negative right here. So we used that property as creating a sum out of that difference there, okay? But then when we had to do that distributive property, we had to do negative 3 times 2p, okay? And then we did, then we added that, then we had negative 3, okay, we could probably put parentheses around that, times a negative 3q, okay? And when we distributed that out, we had, of course, negative 3 times the 2p was negative 6p, and then we just added the negative 3 times the negative 3 was positive 9q. Okay, so every term inside the parentheses multiplied by -1 when we're using the distributive property and finding the opposites. Okay, writing sums as products is the opposite of writing products as sums. Okay, so when we have writing sums as products, instead of distributing, okay, and multiplying, the product is being factored out. Okay, it's being factored. All right. So in this case, we wrote our product as a sum, and we've expanded it. Okay, we've expanded it. But then, if we wanted to take that right here, let's put that up here. We can start with that negative 6p plus 9q. Now, if we wanted to now go ahead and factor this, okay, which is going to be just the opposite of what we just did. Remember, we found our common factor. Okay, so in this case, we are trying to get the inside of the parentheses to both be positive numbers. Okay, positive numbers. What you're trying to avoid is negative numbers inside of the parentheses. So in this case, we'd have to look at, and now we're looking in terms of integers. We're not just talking about positive numbers, but we're looking at what are some of the factors of -6 and 9. Okay, -6 and 9. 3 is one, but also have to remember that not only 3, but -3 could also be used. So if we use a -3, then we can end up with 2p plus, 2p minus 3q. Okay. Now, of course, we have that negative sign right here, but that's a different sign. What we don't have, though, is we don't have a negative in front of the p, for example, for the 2p. Okay, we can factor that out. Now, that is slightly different than 3 times -2p plus 3q. Okay. How this is different now is, it works. It is similar and it is equivalent. Okay, but when we're trying to factor completely, we would prefer to have it written in this form. Anyway, there will be many examples of that coming in the future. So hopefully you are beginning to understand. So see you later.